All right then. So here then is, oops, on the worksheet, what are we on? 7.5b, number 8. So here's what we know. We've got a rifle. We've got a bullet. The bullet is going to get launched out of the rifle. The bullet begins at rest, and then the problem tells us that the bullet exits the gun at 965 meters per second. The problem also tells us the mass of the bullet is 4.2 grams, which is the same as 0.0042 kilograms. And it tells us that between here and here, the displacement is 75 centimeters, which is the same as 0.75 meters. So let me pause there for a minute. That was the intended setup. Again, I am sorry that I did not make it clearer that the gun was being fired horizontal. So everybody good up to there? Okay, so I've already established the velocity. We also need to think about height. So remember, when you do your height, you can arbitrarily choose where you want your height to be 0. Since the bullet's not moving up or down, let's just call the height 0. Follow? All right. And so as you start to do these problems, you sort of get onto autopilot, and anywhere you know your velocity, you should find your KE. Anywhere you know your height, you should find your GPE. So let's take a quick second and do that. So here at this first point, I know my kinetic energy is going to be 0. I know my GPE is going to be 0, which means my total energy is going to be 0. Follow? Okay. Over here, holy moly, kinetic energy, 965 squared times half your mass. I need a calculator to do that, and I was not smart enough to write it down. Oh, there it is. 1956. Everybody cool with how I got that kinetic energy? We know the mass, you know the velocity. It's 1/2 mv squared. Cool? All right. I know my GPE is, the height 0, so the GPE is 0. That means my total energy is 1956 joules. All right. So like I said, everything that I've done up until now has just been kind of autopilot, right? Think about height and velocity at each point. Anywhere you know the height, find the GPE. Anywhere you know the velocity, find the KE. Do as much of that as you can. Good? All right. Then your question becomes, what do I know about my total energy? And there's two possible answers. Either it stays the same, in which case, hooray, it stays the same. That's a useful thing to know. Or it changes. If it changes, find your work. All right? So, in this problem, what do we know about the total energy? Is it staying the same or changing? Changing. There's a change in total energy. There is a change in total energy. We should find it. That's an E. So what's our change in total energy? Well, remember, it's always final minus initial. So 1956 minus 0 gives you 1956. That's my change in total energy. All right, now, the problem, I haven't even said what the problem asks us for. The problem wants to know, what's the force of the rifle? How much force does the rifle exert pushing the bullet out of the gun? Well, our total energy changed, right? So there's one equation that's at the center of this whole chapter, you guys. Remember, if your total energy is changing, the reason it's changing is because work was done by a non-conservative force. All right? And the amount of work that your non-conservative forces do is equal to your change in total energy. Good? So, for us, what's the non-conservative force here, you guys? The gun, the rifle, right? The rifle's pushing the bullet forward, right? So that means for us, the work done by the rifle must equal our change in total energy. Follow? And so now, the other equation that you need to make sure you remember is the equation for work, which is work is force times displacement times the cosine of theta. So for us, the work done by the rifle is the force of the rifle times the displacement. And why aren't I worried about the cosine theta part here, you guys? Yeah, because everything's parallel, right? Your force and your displacement are both that way, right? Clear? So, the work done by the rifle is 1,956 joules. That's got to equal the force of the rifle times your displacement. So divide, and whatever that is your answer. What is it, 26 what? 2607. 2607. All right, so let me pause there for a minute. Questions with it? All right. Part B is basically the same thing, except in Part B, instead of talking about getting the bullet going, we're talking about stopping the bullet. So in Part B, instead of your energy going from 0 to 1956, in Part B, the energy goes from 1956 back down to 0. Otherwise, it's the same problem. Good? All right, Sid, you were craning your neck back there. Are you all good? Okay, I need everybody's attention, but I meant to say this at the beginning of the hour. Did anybody solve this using, by finding the acceleration and using the acceleration to find the force and then blah, 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 blah? I see some nods, all right? So that works, for sure. And for the purposes of this chapter, I want you guys solving these problems using energy. Okay? And the instructions on the test are going to say that. Use energy concepts, all right? So yesterday I did one problem that was set up where you had to use some old equations to solve it. And I kind of wish I hadn't done that problem in retrospect because I think it was misleading, all right? You really should be solving these problems. So this chapter only. No Newton's second law. Please try to solve the problems using energy stuff. Use the current equations. Okay, because that's the whole point of this, is I want you guys to understand the connection between how the force affects the energy. Okay? And if you solve it using your acceleration, then you're kind of defeating the point of the chapter a little bit. Clear? Okay. All right. Any questions on that one? Okay. So let me go back, if you guys are cool with it, and get... What did the survey say? I guess we can check the survey. Let's do 6 and then do 7. Cool? All right. So